When we look at quantum technology and we ask where it is along where its maturity curve, I think obviously we still have a lot to do. Where we've got there's a lot of progress to be made, but I think of it as more, if I was to compare it to the human life, it's in its teenage stage. We've demonstrated things that are beyond classical computing. Now we've got to focus on how do we get algorithm discovery and how do we turn it into practical use case. So we're at the exciting state, everything's open, there's a lot of discovery to be made, but we're definitely at a size where we can do things that are beyond brute force simulation. Like a quantum computer is finally better at being a quantum computer than a classical computer, but to make it better than being a classical computer, we've got to discover a lot of algorithms. A lot of times we try to confuse people with words. So the question about a qubit and what is it compared to a bit, I think of a bit is almost like a handicapped qubit. So a qubit can be in much more superpositions, much more powerful. It can be in both 0 plus 1 in a coherent way, whereas a bit can only be in 0 plus 0 or 1, or you could have some probability mixture of them. So what I think is really more important is where computing is going is making programming a quantum computer much more like language. So the key question is, and this is what we're seeing in AI, all this great inventions of programming just classical computers, you can write sentences and it can be turned into code. So the exciting part about quantum is we can leverage these advances in AI and we can actually simplify it. So most people don't even need to worry about a qubit, and you can just write sentences that turn it into quantum code. The future of computing right now is the most exciting time, because the future is not just making one form of computing faster, it's how are we going to have CPUs, how are we going to have GPUs or AI accelerators, and how are we going to have QPUs all working together in a heterogeneous way. So in my view, right now is the most exciting time for computing, because it's not just making one thing faster, it's making accelerators that do different things much, much better. And how do we come up with algorithms that can do some stuff on a QPU, some stuff on a GPU, some stuff on a CPU? One of the things that we're really looking forward to is we're actually installing in San Sebastian an IBM System 2 next year. This computer is our most advanced, and it's built in a way that we can upgrade it. So we can actually put multiple QPUs in. So you know how I talked about before, we could maybe program over CPUs, GPUs, and QPUs. In the future, we can have many QPUs, many CPUs, many GPUs, all working together to create a much more powerful compute. So our IBM System 2 is the first time we've gone from the System 1, which was a single QPU, to a system that can scale and have multiple QPUs all working together. My dream is to see people come up with new algorithms. Why can't we make cheaper fertilizer? Why can't we make better materials that use less energy? Why can't we make the future of computing not require so much energy to do the computations we want? All of these are possible in a quantum computing world, but the harder question is we don't know what those algorithms are. We've got some ideas, but you can't simulate quantum algorithms with the classical computers. You have to do the work on a QPU, a quantum computer, to be able to do it. So what my dream is why can't we come up with better ways of transporting energy, better fertilizer, more efficient ways of doing calculations, and this will lead to, hopefully, we continue to see computing being fundamental for our progress. So the question of why do we work with so many partners around the world in installing quantum computers, it comes back to that algorithm discovery. So if you look at some of the big companies in the US or even in Europe, take Netflix. It's got an algorithm in there called a recommendation algorithm, and they built a way that people now watch movies based on an algorithm. For quantum to reach its full power, we have to build hardware, and we're building the hardware. But we also have to have algorithms. And the best place to do algorithms, what happened in the classical world, is it first started with scientists coming up with different ways to model high energy physics, condensed matter, all these really fundamental scientific questions. And then a lot of use case, either students or other enterprises that learn about these algorithms said, maybe this applies to this business model. So what we have to do is we have to get scientists using a quantum computer to come up with algorithms that they couldn't do in a classical world, so that we can eventually lead to use cases and things that matter, or come up with something that changes the way society is. And when I look at San Sebastian, you've got the DIPC here, you've got 18 different universities. And when I first visited here many years ago, I was very impressed with all the scientists that wanted to do science using a quantum computer. And so that's one of the reasons why it's important, similar to why we have a few partnerships in Japan, Korea, US as well, Cleveland Clinic in the US, as well as in Germany. They're all trying to use the quantum computer to come up with algorithms.